Okay, so hello everybody, and thank you for attending this presentation. Today we are going to discuss about runtime versus compile time optimizations. Basically, we'll study two approaches. One approach which is called just-in-time compilation, basically happening in Java. And AOT compilation ahead of time, meaning in case of LLVM clang. This presentation is basically the result of George and myself. George can't attend this session. George is the expert on C++ side, and we work together on this presentation. So if you might have some advanced C++ questions out of the topic of this presentation, maybe I might not able to answer them at the moment, but I can reply back to you later on. Basically, I'm a Java guy. What is our agenda for today? I took a bunch of cases and we will iterate through each of these cases, and we will study what's happening under the hood. Under the hood meaning like what kind of optimizations are in charge LLVM, clang, or just-in-time compiler in order to squeeze the ultimate performance. And at the end, we will end up the talk with some conclusions. What was our main motivation for this presentation? Basically, I'm a big fan of this guy, Richard Feynman, the Nobel Prize winner. And I was mainly driven by this code, the pleasure of finding things out. This was my main motivation, my pleasure to find things out. And that's why I decided to study multiple approaches from compiler optimization perspective. Nevertheless, learning based on evidence, it's always better when you have an experiment and you reach some conclusions, and your experiment is based on real facts. This is the best way to learn things by yourself. All of this being said, the key points in this presentation are as follows. I'll try to digging a bit in this write once, run anywhere approach. Basically, it says that I run something, I compile it, and it refers basically to the Java approach. And then after I compile it, I can run it on any platform. This is not possible unless the virtual machine it's in place for us. The second key is to take this kind of optimizations out of the Java and the just-in-time compiler C2 and to compare those with LLVM clang optimizations. Just notice in here, for the ones not quite familiar with Java and what C2 stands for. Basically, in Java, there are two runtime compilers, C1 and C2, and C2, it's better in terms of optimizations. It does the most aggressive and speculative optimizations. That's why I basically bypassed the JIT C1, and I was taking into account on only the C2 because the C2 brings the best performance during the runtime. And why LLVM clang? Because LLVM clang, based on our tests, was better than GCC. There were a very wonderful optimization that clang could do with minus or free level of optimization in comparison with GCC. So basically, that's why we decided to compare C1 and clang in this presentation. And of course, we'll study what means this powerful performance, what it really happens, how they treat different corner cases to take care of the performance. And the takeaway is basically a better understanding in terms of these optimizations from a just-in-time approach to an ahead-of-time approach. Basically, I would, during this talk, I don't want to be focused on Java/C++. It's not my main interest, but my main interest to study two compilers and to spot out their optimizations. That's why, let's say the disclaimer, there won't be a battle between Java and C++. I'm not trying to establish a winner, because there are different compilers. They might do optimization in slightly different ways, and my purpose is just to study and analyze these optimizations. And what this might be a matter of interest. First, for the performance. Performance, it's always a big deal, especially in projects where performance is an ASR, architecture significant requirement, and the ASR, it's quite stringent one. And as I was saying, I took Clang because basically it's one of the best AOT compilers. It's kind of amazing. The experiments that I did with George, it behaved really, really good. And the last but not the least one, Java started to move towards AOT. Since the 9 release, Java added support for AOT compilation. It's quite limited at this stage because they support only on Linux. But the approach is to move and also offer support for both just-in-time and AOT compiler approaches. And here are two comparisons. As you can see, really a huge bunch of optimizations. Also, just-in-time compiler and Clang can do a really huge number of optimizations. Of course, I won't iterate through all of them. I picked up few cases to illustrate how one behaves in comparison with the other. What are the optimizations that are happening? Because also the compilation process, it's quite different. For example, in a just-in-time manner, we have initially the bytecode, which is out of our source code, and this bytecode, it's portable. That's why the initial slogan Wara. But to be able to run during the runtime, you need the virtual machine. And by default, Java starts in interpreter, then it goes and profile the code, and based on the profiling, there is a just-in-time compiler, the C2 compiler. Based on profiling, it generates the native code. In Clang world, the things are slightly different because Clang compiles towards the hardware architecture, and it's split in basically a front-end compiler which maps the code into a high-level representation. It does some optimization, and at the end there is this code generator which generates the code, the native code, so you can take the native code and you can run it against the compatible hardware platforms. So as you can see, two different approaches. That's why I was saying that the main for today is just to study these approaches and not to be stuck with Java versus C++, because Clang is not used only for LLVM, basically, but it's not used only for C++. It compiles any other programming languages. And there is a tendency also on the Java side. There is a project they started to move towards AOT based on LLVM project as well. So it might be quite interesting. The remark before zooming in inside the tests, we can't escape the native code. Only by zooming and inspecting the assembly code, we were able to understand the optimizations, because these optimizations are binary coupled to that specific hardware architecture. So this is the disclaimer. Basically, that the presentation might contain a lot of assembly code, but don't worry about that. I cut a lot of irrelevant assembly, so I try to minimize it in order to be easier to be presented and easier to be understood. And before going into the tests, the hardware specification, you have it on the left side. And in terms of software, I used a lot of, for example, a lot of tools. I used the latest JDK, recently came out, the 9th one. I use a Java measurement harness, which is a micro benchmark basically for Java. JIT is a tool basically which displays the assembly code. On the C++ C++ side, I was using the LLVM clang compiler, C++ Google benchmark, so all the C++ tests were written in the Google benchmark. I used as well Godbolt to inspect the assembly, and I used perf command as well, because in some cases I wanted to take a look on the hardware performance counters, for example, the CPU cache misses, stuff like that. First case from our presentation refers to the sequence sum of n elements. Basically, all the tests are following the same pattern. First, it's a very, very short piece of code. Then the second part, it's the just-in-time compiler C2 shape of it. The third part, it's basically the clang, what clang optimizations did, some benchmark comparisons, and conclusions. So this is the pattern that we are going to follow for each of these optimizations or tests, basically. So sequential sum of n elements array, which it basically says that I have an element, I iterate through these element arrays, and I just do the sum. And at the end, I return the sum. This is Java code, by the way, for C++ guys. We did the same code. We tried to simulate the same code on C++ side. But for this presentation, I put all the code samples in Java. I don't think it's a problem because they are quite easier to be understood. So the benchmark does like this. Benchmark basically measures how much time it takes one operation, means one method invocation, and what kind of optimizations are done under the hood. So if we zoom inside the JIT C2 shape of it, this is the bunch of instructions after a cleaning process. So it starts initially with some initialization. Basically, in this kind of initialization, it for example, initialize the R8 register, it's incremented. This is mainly, if you want, a bit of loop peeling did in advance. The second part, it's scalar preloop. Why it's scalar? Because we don't have here any vectorization support. Vectorizations mean SIMD instructions. Everything it's done one by one, but it's not done until it parses the entire array, and does just only a few cycles. Why is important? It's for CPU caching and a better alignment. That's why it uses this preloop. And the main loop is this one. Inside this main loop, as we can see, it does 8 additions. Basically, it adds 8 integers inside one cycle. This tactic, it's called loop unrolling. So basically, it unrolls the loop in order to minimize the number of jump instructions, and it does 8 by 8. At the end, if the remaining it's less than 8, of course, it doesn't fit inside this scalar main loop. And it does as well some post loop where it adds the remaining numbers which are less than 8. So this is the approach of C2. As you can see, there is no vectorization in all of this stuff. In comparison with clang follows basically the same pattern. It has the main loop. The main loop, it's a vectorized loop, and inside this vectorized loop, it uses XMM registers. So registers on 128 bytes. So basically, inside one of these registers, 4 integers fit, and it does loop unrolling as well, and it does 32 integers per cycle. Why? Because it has 8 additions, and inside each addition cycle, it uses XMM registers. So inside each of these XMM registers, 8 integers fit. So basically, there are 32 integers. So in one cycle, Clang was able to optimize by adding 32 numbers. But what happens if the remaining is less than 32? If the remaining is less than 32, it moves and switches to the L1 loop, where it does 8 numbers, 8 additions per cycle. And this loop is also vectorized, as you can see. But what happens if there are still remainings but less than 8? It goes into the last scalar post loop and it does addition one by one. So basically it was able to optimize by many loops. The first loop does 32 at the time, the second does 8, and there is a remaining, short remaining, which is performed incrementally one by one without any kind of vectorization. If we want to get back and to summarize what we have saw until this point, so just-in-time compiler, this is the loop unrolling pattern. Basically starts with a scalar pre-loop, with a main loop where it does 8 additions, and the scalar post loop one by one, the last one, and clang was powerful in this context because it vectorizes the main loop, 32 integers per cycle. It vectorizes the remaining as well if it is less than 32. And the last one, it does one by one incremental. In terms of comparisons, of course, because just-in-time compiler is not able to vectorize the performance, you have here the number of nanoseconds per operations. And operations basically means one call method invocation. The performance it's slightly not slightly the performance it's better in terms of clang. Clang uses vectorization, and the vectorization is the explanation why it's so powerful in this situation. So just to conclude, Clang uses vectorization for both main and post loop. There is a remaining post loop without any vectorization, and it uses XMM 828 bits registers. In comparison with JIT C2, JIT still does loop unrolling, but again, the vectorization makes a big difference in this. The question that raises, because we saw Clang as very, very powerful, is what happens if the array length it's known ahead of time. For example, let's start running this loop from 0 to 128 elements. And in this case, it's surprisingly wonderful, because what Clang did, it doesn't do any, as you can see here, any loop. It just do 828 integers adds. All of them are vectorized, so no loop, no branch instruction. Everything is linear, which leads to the conclusion that it increased the instruction cache size, because having all of these instructions without any loop increases the instruction cache size. But during the performance, during the runtime, the performance it's better. So it ended up in this kind of powerful, very powerful optimization. Let's get back a bit and say, okay, we saw the just-in-time compiler C2, and the question that we might think of is, okay, it doesn't do any vectorization, and of course the answer is yes, it does. But specific in this case of iterating through an array and computing the sum, it doesn't do vectorization because the Oracle guys explicitly chose to disable the vectorization. So in this case, the vectorization is not supported. But let's see what are other cases when just-in-time compiler does vectorization. First one is when you have, for example, two arrays. This is the setup. You initialize both of these arrays and you compute the sum. So you have basically C equals A and B. And in this case, if we take a look over the code which was generated, you can see it's even powerful because it uses YMM registers, 256 bits. So basically in one, this kind of loops, just-in-time compiler was able to do 32 integers. So it was able to do 32 registers per loop cycle. And another case where it does optimizations like this is where you have, for example, an array and you iterate through it like in this, and each element out of that array you increment by a constant value, for example. In this case, it uses an even more powerful optimizations because the main loop cycle, it's split, it's unrolled, and for each cycle it does 64 adds. So basically 64 integers additions are handled by loop cycle. In terms of vectorization loop pattern, in this case, for the JIT, when it does vectorization, it goes into a scalar preloop. It's basically for the CPU cache, some alignment stuff. The main loop was vectorized, and there were 64 additions per cycle. If the remaining it's less than 34 bar greater than 32, it does this one, and then if the remaining it's still less, it goes into this scalar post loop. So basically it's the same approach as we saw on the clang, the first case, but it's even powerful because it is based on YMM registers. In terms of comparison, this time the just-in-time compiler it was better because on the same source code, computing the sum of those two arrays, one array size being 100 millions, for example, it was like 62 milliseconds per operation in comparison with clang. Basically, it was one order of magnitude better just-in-time C2 compiler. Why is that? Because I took a look over the clang code, and the clang is not using the 256 registers, but it uses 128 registers. So basically, the number of additions per loop cycle was smaller in case of clang. This might be an explanation for these figures. The next case is the one from sequential sum of n integers. So basically, what we have in here, we compute the sum from 1 to n inside this loop, and we return the sum. And what just-in-time compiler does, initially it starts again with some loop peeling. Basically, it peels out of the loop the first iteration. It does as well some initializations, and it continues with the main loop. Inside this main loop, it does 16 additions per cycle. So basically, in this loop, it adds the first 16 numbers. The next cycle of the loop adds the next 16 numbers, and so on. So basically, it adds 16 by 16 until it reaches the n size. Of course, there is a remaining also in this case, because if the loop it's not doesn't divide, and there is a remaining, the remaining is handled by another scalar preloop. It's basically the same pattern. In terms of clang it's wonderful, because what clang says, is able to spot the formula, and it doesn't do any loop peeling, it doesn't do any unrolling, it has no dependency on n. So basically, it uses this kind of formula, n multiplied by n minus 1 over 2 plus n, to compute the sum of n integers. In terms of performance, of course, clang it's way better, and the just-in-time compiler it's dependent on n size. Bigger the n, less throughput we have during the runtime. So to conclude this kind of tests, LLVM clang was able to recognize the pattern as we saw and perform that wonderful optimization. Just-in-time compiler, even it did peeling, loop unrolling, wasn't able to give better optimizations than that LLVM clang, because it used the reduction formula basically. And the most important one is that in this case, the performance in Java from just-in-time compiler C2, it's n size dependent. Bigger the n, less performance, or slower it is. The next case it's for the fields object layout. What is this fields object layout meaning? Basically, I took two approaches. I took an approach using a vanilla class, and inside this vanilla class, I have two fields, X and Y. I have the second approach using padding. Padding means between X and Y, I edit explicitly 8 longs. Why 8 longs? Because the CPU cache line on my architecture was 64 bytes, and also in modern architectures, most of the commodity hardware have these 64 bytes in terms of cache lines. So I've added this padding just to be able to bypass the one cache line and to be spread across multiple cache lines. And the third case, it's similar to the padding one, but in this case, instead of merging X and Y inside the same class, I did this extends. Why is that? Because in terms of Java, it's able to reorder the fields. So basically, the order you declare them at compile time, it's not the order they are during the runtime. Why? Because Java reorders the field to minimize the object footprint and to do a better alignment. So for example, in this case, even if the programmer declares X, longs, this sequence of longs, and Y, the Java reorders this, so it collapses X and Y, and then all the longs are added. So in this case, the footprint of padding is 80 bytes. And in the last case, because we have extensions, it is not able to reorder the fields from the child with the parent class. So in this case, what it does, it keeps the same order, for example, Y after this bunch of longs, but it adds padding in between this short and the first long. Why is that? Because all the fields should start with at addresses divisible by 8. The second approach was with structs. So with structs, it's kindly the similar approach, but default clang doesn't do any fields reordering. It just adds padding. The vanilla case is exactly like the Java case. The padding one, as you can see, it's XY. In this XY, you have XY. And after the Y and until the first long in this sequence, you have a padding. Why is that? Because also the compiler adds paddings for the alignment. Keep in mind that if for Java, it's basically the same footprint in Clang or C++, it's dependent. Every compiler can and on specific platforms can do padding, so it's not relevant on all the platforms. It was on my target architecture platform, this kind of object layout. And in this case of base, this was X, Y, and the longs in the middle. And as I was saying, Clang doesn't do any fields reordering, just add paddings in between to have a better alignment. And in this case, we have X padding of 6 because the first long should start at an address divisible by 8. And then it goes, it lays out all the fields. And it couldn't finish at 74 because 74, if we finish this hierarchy struct as 74, we might have a misalignment in case there is another hierarchy struct after it. So we need to also do a padding to be multiplied by 8, basically. Having all of this said, let's zoom inside the CPU cache lines. In modern architecture, the cache line is 64 bytes. So having this in mind, let's see how many fields from Java and C++ fit inside one cache line. In Java, the vanilla, only 4. Why it's only 4? Because as we saw in here, this blue, Java has the object header. We can't get rid of object headers, and these object headers impacts the footprint for the Java instances during the runtime. So that's why, for example, in case of vanilla, which has 16, we have only 4 instances fit the same cache line in comparison with the struct. The struct doesn't have any header, and that's why there are slightly more. In case of padding and hierarchy, the things are the same, one of each case, but there is a difference in terms of X and Y fields, because in case of padding, X and Y fits on the same cache line, and in case of hierarchy, in Java, they are on different cache lines as well, and in struct the same on different cache lines, because I explicitly created the data structures to behave like this. So having all this context in mind, let's see how I did the test. So basically I created 2 tests, and inside each test I took the vanilla, the padding, and the hierarchy example. So I've created arrays out of 2K elements, and I iterated them, and I created the sum. And basically, in this kind of approach, if you are not CPU cache friendly, you pay the cost of cache misses and so on. So basically, let's see what we have get. In case of padding and hierarchy, there was around the same performance between C2 and clang. Why? Because both of these 2 objects had the same footprint, and in this case X and Y fall on the same cache line. So accessing X, next time we access Y, it was already on the same cache line, so we didn't pay the cost of the CPU stall. In case of hierarchy, it was slightly slower, because accessing Y doesn't guarantee that X doesn't guarantee that Y it's on the already in the cache. So probably there was some more cache misses, but again almost or the same performance. The things are slightly different in case of vanilla, as I was saying, and it is caused by the Java header. In this case, it's 12 bytes, so we pay 12 bytes. So 12 bytes are laid out into the same cache line, and it minimizes the number of instances. That's why in this case, clang and C++, basically, this is not valid only in clang world. It's better because they don't have object references, which occupies the cache lines. And all of these conclusions, we already discussed them. Basically, if we would have in Java a smaller footprint in terms of object headers, we might end up with almost the same performance. It's not a big difference in terms of performance. Nevertheless, big gain in Java is that it reorders automatically the fields. So this is quite nice. With clang, by default, it's not possible. You have to explicit do some workarounds in order to reorder the fields, to explicitly say to the compiler that. Null checks, this is the next category of cases. Basically, what I have tested is a method which receives an object and returns that value if it is not null multiplied by 42. Otherwise, it returns 0. The first case scenario was I called this method all the times without any null value. And what just-in-time compiler did, the C2, he was able to spot out that all the values during the runtime were not null values. So he was able to get the int value and to multiply that int value by 42. So as you can see, even if the programmer put an explicit check, we don't have any explicit check in here in the assembly code generated. But what we have is an implicit exception. What it says that he is not 100% sure that during the runtime there are no cases where hot method it's called with null values. But if that happens, there is explicit null check handler, which calls the uncommon trap. Basically, this is the kind of optimization the C2 does. If he figures out that during the runtime, the code follows the same path, it optimizes for that path and puts uncommon traps for the other paths. In case the other paths or branches in the code are hit, the uncommon trap is called, and it de-optimizes the code. In case of clang doesn't do any uncommon trap. It tests if the value is null. If it is null, returns EX. It does basically XOR. And if it is not null, it multiplies by 42. So it doesn't complicate the things. It just does the explicit null check because the developer put the explicit null checks at the code. In terms of performance, not quite a big difference, frankly speaking. C2 was 2 nanoseconds to the 3 nanoseconds, clang 2 nanoseconds. Nevertheless, I couldn't find a way for clang, for the C++ Google benchmark, to give me results with decimals. So I don't see any big difference in this kind of context. And the conclusion out of this text was that JIT C2 relies on segmentation faults. As we saw, he doesn't do the specific null check, but when it happens, a segmentation fault happens. The hardware throws segmentation fault, it is caught by the OS, it is propagated inside the JVM, and the JVM is able to see, okay, that one is a segmentation fault because I made this optimistic assumption. Let's fall back and de-optimize this kind of optimization because there is a null call for the method, a method called with null values. But what happens if we, for example, call with null values and not null values? The code is basically the same, only the test scenario is different. So in this case, just-in-time compiler did the same as clang did. Basically, it tests if it is null. If it is null, returns 0. Otherwise, does the multiplication. So it's exactly like clang did by default. And in terms of performance comparisons, again, still not a big difference. So it was like 2.5 nanoseconds per operations in comparison with 2. I can't say there is a big impact on modern hardware calling, doing a branch check, the assembly code versus just going and optimizing a branch and putting an uncommon trap, because the cost that you will pay will be when you hit that uncommon trap, basically. Lock coercioning is the next technique that we did. Basically, lock coercioning says that if I have this kind of stupid implementation, one method, and inside each method I have a bunch of, for example, synchronized blocks, for example, 10 blocks, and inside each blocks I get one by one, I compute the sum. Just-in-time compiler, it's able to spot out during the runtime that there is no sense to do 10 synchronized, to perform 10 synchronized blocks. It does only one, and at the end it just adds in a sequential fashion without any lock all these numbers, so returning the result. In comparison, clang, it's not able to spot that out. You know, what does clang? It just does the 9 useless locks, as you can see, and inside the last synchronized block, it does all the math and returns the result. In terms of performance, this time just-in-time compiler, it's better because he was able to remove the unusual synchronized blocks. Clang doesn't do that. And the performance in JIT specific in this case was like 3 times faster. Also because, and more than that, the execution time is dependent on the number of the locks in C++. And in Java, now it optimizes, the C2 optimizes. And this kind of optimizations comes from the history because initially the Java developers were not were not very used with the synchronization, and in practice they abused of synchronization, and in synchronization impacts performance. By default, in C++ world, the performance, the programmers, sorry, should be more aware, and they should not abuse or use in a more conscious way the synchronization. That's why probably they don't do this kind of optimization, or they didn't pay any attention on it. Lock elision, it's the next one. It's very similar to the previous one, but this time I have the lock object declared inside the method, and I do the same 10 synchronized blocks, and at the end, inside each block, I compute the sum, incrementing by value, and at the end, I return the value. And what I have, C2 removes all the locks. It does the sums in a sequential fashion without any lock. In clang fashion, there is no lock elision. It does 8 useless lock, and inside the last block, it creates the sum and returns the sum. Again, the performance was better in JIT C2 in comparison with clang, because the clang also in clang or C++, the number of blocks, synchronized blocks, depends, and they impact performance. Just-in-time compiler, it's able to spot that that the locks are useless based on the scope of that lock. So if it has a local scope, and if it is inside the current thread frame, it doesn't make sense because there is never contention on that lock, so just remove it. Virtual calls, it's another kind of optimizations. Let's suppose I have, for example, one parent class, and I have one implementation for that. And my implementation just overrides the method compute. The algorithm is quite simple. So I've created these tests, and inside this test, I basically call a method compute, and for that method compute, I send the instance and the parameter. And what is happening? Inside the method compute, I'm just doing a multiplication. So basically, in this case, I'm doing multiplication between 3 and 17, but I'm calling compute with the base class. Nevertheless, during the runtime, I have an instance of ELG1. And what C2 does, C2 is able to spot this out and doesn't do the vtable lookup anymore. It removes the virtual call, it inlines. In this case, it just do the multiplication, basically, and returns the result. So these kind of calls are called monomorphic calls. In this case of monomorphic calls, just-in-time compiler is able to inline them, and there is no uncommon trap. There is no any assumption from the just-in-time compiler C2 perspective there might be another optimization which might crash, which might be called and crash. The second scenario is when I have two implementations. So I have a parent class extended by 2, and I basically do the same. I call the compute method, and twice with different instance at runtime. And one computes 3 multiplied by 17, the other 3 multiplied by 19. And in this case, just-in-time compiler, it's able to see that there are 2 implementations during the runtime, and it does the check. For example, if it is an instance of ELG2, does a jump in here to L0 and do the multiplication by 19. If it is an instance of ELG1, continue and do the same as we did before. Basically, multiply that value with 17. But if there is an instance, neither ELG1 nor ELG1, go and hit this uncommon trap, because if he might think that if there might be a third or the fourth implementation, this uncommon trap might be hit, and it might get into the optimization stuff. So in this kind of bimorphic calls, there is an uncommon trap, but also just-in-time compiler was able to inline both implementation. In case we have 3 implementation, it's the same. The third implementation does 3 multiplied by 23, for example. Just-in-time compiler don't do any inlining, it doesn't use any uncommon trap, just perform the virtual call, which is costly because it needs to do a lookup in the virtual table. And on the other side, Clang was incredibly smart in this context because he was able to see that all these kind of instances that we were executing during the runtime, and it was able to fault to a constant. So as you can see, in case of monomorphic run, it returns a constant, the same for bimorphic and the same for megamorphic. So it was incredibly fast, even ahead of time. And of course, the performance says that. In case everything, it's around 2 nanoseconds per operation. But in case of just-in-time compiler, the performance, it's bigger and bigger with the number of implementations. So in this particular case, Clang saw the optimization and bypassed basically the vtable lookup. In case of JIT C2 even, it did inlining, it did uncommon traps. He wasn't able to do the same powerful optimization. And of course, in Java, in general, you pay for the number of implementations. So more implementations you have, if the compiler is not able to inline the code, you pay the cost for the during the runtime for the execution. Scalar replacement, it's another interesting technique which basically says, for example, if I have one huge loop, and inside this loop I iterate through it and I create objects, and I just create an object basically for nothing because I have a sum which says count all the objects.id, and the ID it's my value from here. So the value is 1 in our case. Basically, my loop repeated like 1 million times. So in this case, what did C2? C2 was able to spot the pattern. So initially, he took the value, he put it into R11, and it went in the main loop, and inside this main loop, it did 16 additions per cycle. So it's 16 plus 16 plus 16 until it reaches to a certain size, and if the end size it's not multiple of 16, it continues with the post loop where it does 1 by 1 until it reaches the 100 millions. In case of Clang, there is no loop. The Clang was able to spot out the pattern and to return by default the sum of everything. So incredibly smart optimizations. In terms of performance, of course, Clang spent around 6 nanoseconds per operation because it's just a return. In case of C2, JIT, because he couldn't spot out the pattern, he couldn't fold the result. The performance was slower, and of course it's dependent on n. So bigger n you have, slower it is. I mean, slower just-in-time C2 is. And here at the end of the talk, I have some conclusions after all of these test scenarios. So basically, as I was saying in the beginning, there is not a battle between C++ and Clang. Nevertheless, Clang, it's a very interesting and powerful compiler. Even it compiles ahead of time. It does a really good optimizations, very powerful optimizations. Just-in-time compiler, it's interesting, and it helps because of the profiling information, as we saw for the locking examples. it behaves better than Clang, and it's normal because he has the runtime information. So also this compiler, it's good. And the third cases where you have like optimizations that are in the same way, for example, loop unrolling with vectorization, the null checks, there is almost the similar performance in these two cases. So yeah, basically these are the conclusions, and we are reaching our end of talk. Thank you very much, and if we might have questions, I will be glad to answer them. Sorry, can you recommend a good source of information about just-in-time compiler? Yes, I can recommend you a good source of information. There is an amazing video sessions by a guy from Azul. It's called Hawkins. If you search on Safari, because we have Safari subscriptions, and if you search on Safari for Java performance, you will see a series of just-in-time compiler optimizations that by Hawkins, the guy from Azure. Unfortunately, I can't tell you by heart the title for that sessions, but if you can just type on Safari Java performance, you'll see the videos. You'll find them out. Okay, other questions? I can understand LLVM, it's kind of backend, and for any front end, you can use some lang Scala to work with LLVM. So LLVM first, the project has the clang for C++. It uses a front-end compiler, so basically you can inject any kind of code in that compiler. So you can run, for example, Python with LLVM, C++, whatever. In Java, there is an option to move towards LLVM clang, but nevertheless, the back I won't call it a backend compiler because the optimizations that are done are specific to the platform and they are done ahead of time. But indeed, it's a first step. It's a front end which does a high-level interpretation on your code. Then it goes into the optimizer and it generates the code particularly to that platform. So could you possibly share the C++ code too? Yes, it's possible. We have a Bitbucket repository. I'll make it public for the reads, and I'll share it with you. Definitely, because also under the same repository, it's Java code as well. I'd be interested to perform some comparisons on some string processing examples. Yes, why not? Because also string, it's quite interesting, especially in Java. There were some. It's not a question, maybe it's a recommendation. In Java, there was a lot of refactoring on strings, and there were a lot of optimizations. It's a very interesting topic indeed. So we can have an entire presentation only comparing strings in Java in different implementations and optimizations. I agree, it's a good spot. But it's not, I mean, it's not very straightforward because there are a lot of things to take into account. Yeah, comparison on hash tree structures. Yes, this one goes hand in hand with memory access patterns and CPU and hardware prefetchers. Yeah, this one, it's a good hash versus tree. I mean, maps versus trees when you do the memory layout comparisons, when you do the data access patterns. This is on my to-do list, frankly speaking, because I'm working on some big notation in modern hardware. So it's quite interesting, that's one. So yeah, there are plenty of things to try. You can try on your own at least. Yeah, it's quite interesting. As I understood, there is no difference in the compiler. It just depends on the abilities on the compiler to read patterns. Yes, I would say yes. I would say during the runtime, if both compilers optimize, there is not quite a huge difference. What pays Java for, it's for the object reference, as you saw, the memory layout, which is not quite compact, and C++. And yeah, basically these are the things. But if both of the compilers can optimize for, you saw the case with vectorization, you saw the case with null checks, there is not a big difference indeed. Nevertheless, C++ and Clang are deterministic because they don't use profilers. So if you rerun the test again and again, you're on the same target architecture, you might have the same performance, which in Java and JIT C2 it's not the case. I think I understood. Yeah, I think I answered your question as well. So basically, yes, if both can do the same optimizations, there's no difference in performance. It's a myth. C++, it's always faster than Java. It's a myth, really. As you saw based on this presentation, it really depends on the patterns and the optimizations. Okay, guys, anything else? On the Q&A channel, I also covered the hash/tree structure. Yeah, it's a good topic. It might be included in some bigger notation complexity in terms of hardware performance. I covered that as well. Have you found, yeah, I missed this one. Have you found any bugs during optimizations while research and play with both? Yes, I found, especially in just-in-time compiler. Just-in-time compiler has bugs. I won't call them bugs, I call them at this stage restrictions. From my perspective, just-in-time compiler, it's still there is still room of improvement. Yes, for Clang, I couldn't see any bug. But based on the test that I did, no, I see differences between Clang and GCC. So that's why I decided to go with Clang. It's better, but a bug in Clang, no, I couldn't find. It's incredibly smart. Okay. Okay. Still 61 participants in the channel, quite a big audience. Thank you guys for all. If there are no other questions, I would thank you again. Have a nice weekend, have a nice day, and hope to see you soon. Nevertheless, if you might have questions, send me a mail on the company address, ibalosin@laxsoft, or on my Twitter account. I reply to you, and I'm keen on discussing performance topics anytime. So have a nice day, and talk to you soon. Bye bye.